Okay, we're going to look at problem number 12-64 out of your textbook, and it says a jet bike is moving along a straight road with the speed described by the V versus S graph that's showing up down here, and we've been asked to construct the acceleration as a function of position graph. Now, given that this graph, and they've given the picture of the curve, and they've also given us the equations of the curve in the problem statement. Now, the key thing is recognizing that we have V of S and we want A of S. Is time involved anywhere in this problem? It is not, so we're going to be extremely tempted, again going to the upper left-hand corner of the equation sheet, to use, I think, the ADS equal VDV form. And so to proceed ahead with the solution, and this is the kind of problem usually when the solution is presented as a graph, it's an erratic motion kind of problem where the equation of motion changes, and we simply have to do the math and make sure things splice together correctly. Okay, and so looking at this particular solution, we're going to work with this section of the curve first, where V is equal 5s to the 1/2. And so taking ADS equal VDV and rearranging it by bringing the ds to the other side, we're going to have A is equal to V times VDVS. Now, we have V is equal to 5s to the 1/2. The derivative, this is the derivative of V with respect to S, and so that's quite easy to get. We simply have to take the derivative of this thing, and the derivative of this thing is 5/2 times S to the minus 1/2. Okay, and it turns out that the S to the positive 1/2, the S to the minus 1/2 cancels, and we end up with a 25/2, or we end up with the acceleration as constant. Isn't that interesting? So in this region, acceleration is constant, and if we graph it, we'll go down here and generate an A versus S graph, and the first piece of that graph is A equal 12.5, a constant, and that will be true out to a S value of 225. Then the next thing is we'll take our second part of the erratic motion, where V is minus 0.2 S plus 120, and we'll do the same thing. So we will again use A ds equal VDV, moving the ds to the other side and plugging in the V as given, and then taking the derivative dVds of this V of S. Get a 0 out of that constant term, we get a minus 0.2 right there, and multiplying these two terms together, we get that acceleration is equal to 0.4 s minus 24 meters per second. And so we need to calculate a few data points for this thing. We do notice that that's a linear term. It's a straight line. We'll be drawing a straight line. So we need to evaluate A at 225 and at 525 to know how to deal with that straight line. And so plugging in S equal 225 and 525 into this equation, we get a minus 15 and a minus 3. So bringing that to our graph, at S equal 225, we plug in the minus 15, and at S is equal to 525, we plug in the minus 3, and so our acceleration as a function of position is a constant, followed by a step change into a linear term. Now, we don't really know what happens after that, so we just sort of put a stop mark right there. And that would be all of that problem.